Greetings, Chem 2 students. Mr. Keister here with you again today. This is the video for Thursday, December 10th, 2020, which is our scheduled 77th day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do nows, see what our schedule is for today. Today we're going to pick up page 100. Wow, 100 pages in the first semester binder. Getting a little thick there, I believe. Double replacement reactions and solubility. Yesterday we looked at the activity series handout. Now, does the term Lick Bakanamaga als Infini mean anything to you? Hopefully it does by now. All right. We looked at the activity series. We also had an assignment over single replacement reactions, which was page 99. We also picked up our big review packet for our second one for the fall semester. Talk about that here in a second. So your homework from yesterday was single replacement reactions assignment. Hang on to that one. I'm not going to collect that. All that stuff's going to appear on the review that you have with you already. So I'm not going to collect that particular one. However, make sure you check your answers so that you know how to do it right. We talked about a lot of stuff yesterday in regard to single replacement reactions. We talked about the fact that the compounds in solution ionize or split up when dissolved in water. And we talked about how we determine spectator ions and how we determine a net ionic equation. So a lot of stuff yesterday, very important stuff that you need to know. So make sure you double check that. Answer key, of course, if we're here in school, it's here on the board. If you're at home, it is on the answer keys page in Canvas. So today we're going to move on to our next type of reaction, learn how to identify double replacement reactions, starting today. We're going to take a look at solubility. This is kind of a 2-day lesson with 2 separate assignments. So we won't finish the entire lesson today, but we will finish it tomorrow. So the assignment today that you picked up will be due tomorrow, and then we'll pick up a second assignment over double replacement reactions tomorrow. Okay? And then the last thing, your review. So your fall semester quarter 2 review is due this coming Monday, December 14th. Hopefully you are already well on your way working on that thing. Just like the quarter 1 review was, this one is also worth a lot of points. It can be a real grade changer, folks. So put your best effort into this one. Besides that, of course, this is the material that's going to show up on the final, as well as the material from the first quarter review. There'll be no answer key available for this one. So again, make sure you are working efficiently and accurately. Check with your classmates or friends. Can help you find mistakes and get them ironed out before you turn them in. All right. So again, this is worth a lot of points. So make sure you put your best effort into this one. So I believe we are ready to begin today's lesson. So let me change the screen. Okay. In a double replacement reaction, positive ions and 2 ionic compounds switch places with one another, forming 2 new ionic compounds. All right. And the 2 reactant compounds are always in solution. All right. The reactant compounds are always in solution. So here are our 2 compounds that are our reactants, our beginning reactants. And so these are always AQ. All right, these are always AQ. What happens here then is the positive ions, which in this fictitious reaction are A and C. Those positive ions switch places. And so now we form 2 new compounds. All right. Now, what state of matter are these 2 new compounds? Well, that's what we're going to determine today, or how we figure that out. Okay. And so A now goes with D and C goes with B. All right. So the general format then is compound in solution plus compound in solution yields compound, not sure state of matter, we'll determine that, plus a second compound, not sure state of matter, we'll determine that. So again, each one of these types of reactions we've looked at over the last several days has its own unique characteristics. They all look different, and so you should be able to tell them apart fairly easily. All right. Now, a reaction only happens if. Well, what does that mean? That means it's possible there will be no reaction. Remember, with single replacement reactions, we had the possibility of a no reaction. That, of course, was based on the activity series. In double replacement reactions, we also had the possibility of having a no reaction, but for totally different reasons. All right. A reaction only happens if, number one of the products is a precipitate, meaning it is a solid. All right. We call that a precipitation reaction. We're going to get into those very more specifically tomorrow. All right. Secondly, a reaction happens if one of the products is water. All right. One of the products is water. So here we have a solid. Here we have H2O liquid is one of those two products. This is called an acid-base neutralization reaction. All right. And number three, one of the products is a gas. All right. Well, if it's a gas, it's probably a molecular compound, and most likely a polar one. All right. So this would be a molecular compound not soluble in water. All right. Not soluble. Remember, these are both solutions. All right. If one of these products is a gas, that means it's going to be a compound that's not soluble in water. All right. So if one of these three things does not happen, then our double replacement reaction is then a no reaction. All right. Got to be one of those three in order to have a reaction occur. All right. So let's go on to the next page. We're going to look at solubility. If a solid ionic compound is soluble in water, all right, it's soluble in water, and that means that it dissolves completely and forms an aqueous or aqueous solution. All right. We're going to determine that by what we call the solubility rules. There are some rules of solubility that we can follow so that we know if something is soluble in water or not. Soluble compounds in solution will have an AQ next to them. All right. If they're soluble, then they're AQ. All right. For example, sodium chloride, ammonium bromide, potassium sulfate. All those compounds are completely dissolvable or soluble in water. And so once that is done, those compounds go into solution, and we put an AQ next to them. If a solid ionic compound is insoluble in water, then that means that it does not dissolve and it will remain a solid. All right, so if you put it in water, nothing happens. All right, it just sinks to the bottom. All right. Well, again, we'll check the solubility rules for these compounds. Insoluble compounds will have an S, as in solid, next to their formula. For example, silver chloride, lead 2 sulfate, and magnesium carbonate. Those three compounds do not dissolve in water, all right? And thus, we have an S next to them. So now so how do we determine what's soluble and what's not? So we know what to put next to them, all right? Is it an AQ or is it an S? Well, we have some rules. They're called the solubility rules. There's not that many of them. They're not that difficult to remember, but you do need to remember them. So this is something you're going to have to memorize, all right? So just like we had to memorize the activity series for metals yesterday and also for the halogens, we also are going to have to memorize now for double replacement reactions the solubility rules. I kind of got them lumped into three general categories. I think that makes them easier to remember. All right. First category is always soluble. And this is the most important rule, all right? You don't remember anything else. You want to remember these, all right? This is the number one rule. All right. Number one, it outweighs all others. You'll see what I mean by that as we talk about solubility in general tomorrow with our double replacement reaction. So, all common ionic compounds that contain a group 1A metal, a group 1A metal ion, or the ammonium ion, or the nitrate ion, or the acetate ion, are always soluble. Always. So if a compound contains a group 1A metal, sodium chloride, potassium sulfate, lithium bromide, rubidium carbonate, doesn't matter. If it's got a group 1A metal in there, it will dissolve in water each and every time, all right? Always soluble. If the compound contains the ammonium ion, ammonium chloride, ammonium bromate, ammonium sulfate, ammonium phosphate, ammonium carbonate, if it's got ammonium in there, it's soluble, all right? The nitrate ion, so sodium nitrate, magnesium nitrate, iron 2 nitrate, aluminum nitrate. If it's got nitrate, it's soluble, all right? Acetate, well, here again, potassium acetate, magnesium acetate, zinc acetate, aluminum acetate. If it's got acetate, it's soluble. So remember that. Group 1A, ammonium, nitrate, acetate. If any one of those four is in a compound, it's soluble. Okay? Guaranteed. Second rule, almost always soluble. Almost always. Almost always. Emphasis on almost. All right, let me advance this up. We can see it a little better. This is also called the chloride rule. All right. In fact, I normally call it chloride, bromide, iodide rule. All common ionic compounds that contain chloride, bromide, or iodide, Cl-1, Br-1, I-1, are soluble in water, are soluble, except those that contain the silver ion, the mercury 1 ion, which is actually Hg2 plus 2 or Hg2 2 plus. This is the mercury 1 ion. Note that it is a diatomic ion, similar to peroxide, O2 minus 2. All right. Hg2 plus 2 is mercury 1, or lead 2 as their positive ion. So let me explain that. All right. So all common compounds that contain chloride, bromide, or iodide are soluble unless they contain one of those three positive ions. So, for instance, let's talk chloride. So calcium chloride is soluble. Aluminum chloride is soluble. Iron 3 chloride is soluble. All right. Sodium chloride is soluble. Of course, it would be soluble anyway because sodium's group 1A. But silver chloride, mercury 1 chloride, and lead 2 chloride are insoluble. All right? They don't dissolve in water. Those three. Same rule applies to bromide. So silver bromide, mercury 1 bromide, lead 2 bromide, not soluble. All other compounds that contain bromide are soluble. All right? And the same goes with iodide. So that's the chloride rule. All right? Which also includes bromide and iodide. The next rule is very similar. All common ionic compounds that contain the sulfate ion. This is the sulfate rule. Are soluble in water except those that contain those same 3 positive ions, silver, mercury 1, and lead 2, and also strontium and barium. All right? So, quick review. All compounds that contain sulfate are soluble with the exception of the 3 we mentioned before plus barium, strontium. So, potassium sulfate, soluble. Well, of course it is. That's got group 1A, potassium. Magnesium sulfate, soluble. Calcium sulfate, soluble. Copper 1 sulfate, soluble. Aluminum sulfate, soluble. But silver sulfate, mercury 1 sulfate, lead 2 sulfate, strontium sulfate, and barium sulfate are not soluble. They are insoluble. They do not dissolve in water. So again, the other 3 that we mentioned before, same with the chloride rule. All right? Silver, mercury 1, lead 2. And in addition to those, barium, strontium. Okay? If those 5 positive ions are with sulfate, that compound's insoluble. If it's any other compound that contains sulfate, it is soluble. All right? So those are the almost always soluble rules. All right? The chloride rule, which includes bromide and iodide, and the sulfate rule. Okay? Remember, though, what's always soluble? That's the important one. That's the most important one. Group 1A, nitrate, ammonium, acetate, always soluble. Okay? Last rule. This is the almost always insoluble bunch. All right? So these are almost always insoluble. All right? So the first one here is the carbonate to phosphate rule because it's the same for both. Carbonate phosphate rule. Remember, carbonate is CO3 minus 2. Phosphate is PO4 minus 3. Boy, remember, you got to remember your ions here, folks. Just like always. All common ionic compounds that contain carbonate or phosphate are insoluble, except those that contain an ammonium or group 1A. Remember why? Because ammonium compounds and group 1A compounds are always soluble. That first rule trumps this one. It's like, playing cards, right? I don't care if you have an ace of clubs, right? If hearts is trump, the 9 of hearts is taking your ace of clubs, all right? Well, this same deal here, all right? If it's got a group 1A or ammonium in it, I don't care whatever else is insoluble. That one's soluble, all right? So, carbonate or phosphate, they're all insoluble unless they have a group 1A or ammonium in them. So let me give you an example there. So let's see. Magnesium carbonate, insoluble. Calcium carbonate, insoluble. Cobalt 2 carbonate, insoluble. Aluminum carbonate, insoluble. Zinc carbonate, insoluble. But ammonium carbonate, soluble. Potassium carbonate, sodium carbonate, lithium carbonate, soluble. Because they have ammonium or a group 1A in there, all right? And the same exact rule applies for phosphate, all right? Same exact rule applies for phosphate. And then the last one. This is the hydroxide sulfide rule. It's very similar to the last one, all right? Very similar to the last one. All common ionic compounds that contain hydroxide, which is OH minus 1, or sulfide, which is S minus 2, are insoluble in water, except, again, the ammonium or the group 1As. If ammonium or group 1A is with the hydroxide or sulfide, it's soluble because ammonium and group 1A are always soluble. As well as calcium, strontium, and barium. Those are also soluble, all right? So, let's see. Let's just use hydroxide then as an example. Okay, so sodium hydroxide is soluble. Why? Got a 1A in it. Ammonium hydroxide is soluble. Why? It's got ammonium in it. All right? calcium hydroxide, strontium hydroxide, and barium hydroxide are also soluble. But any other hydroxide is not. All right? Magnesium hydroxide, aluminum hydroxide, iron 3 hydroxide, zinc hydroxide, blah, 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 insoluble. And the same exact rule applies for sulfite. All right? So those are the solubility rules. We have those ions that are always soluble when found in a compound. We have compounds that contain, and remember those, the always solubles, group 1A, ammonium, nitrate, acetate. Then we have the compounds that are almost always soluble, chlorides, including the bromides and the iodides, and the sulfates. All right? They're almost always soluble unless they have silver, mercury 1, lead 2. That's for chloride. And then for sulfate, that also includes strontium and barium. All right? Then we have these, the almost always insolubles. All right? We just went over those. So, got to know all those. All right? Got to know all those. So let's do a little fact checking here on these examples and see if we remember what's what. And then we'll move on to your assignment. So, example 1, we're going to check and see whether these compounds are soluble or insoluble. All right? So, number 1, KBr, soluble or insoluble? Well, I would hope you would recognize that K is a 1A metal, and so that's going to be soluble. All right? That's so well, soluble. Don't have to write the whole thing out if you don't want to. Also, the bromide rule, which is the chloride rule, says they're almost always soluble except for a few exceptions. Of course, 1A trumps that rule anyway, so it's always soluble. So the next one, number 2, ammonium sulfate. Well, here again, ammonium, always soluble. All right, so that compound is soluble. Third one, aluminum nitrate. Here we go again, rule 1. Nitrates are always soluble. All right. Got to remember those always solubles. That is a critical rule to remember. Okay, calcium phosphate, number 4. Okay, so phosphates are almost always insoluble. Is calcium an exception? The answer to that is no. All right. The phosphates are always insoluble except group 1A or ammonium. Calcium's not 1A, it's 2A. All right, and certainly not ammonium. So this one is insoluble. Insol. That's all you got to write there. Number 5, sodium carbonate. Well, sodium's 1A. You said, no, wait a minute. Carbonates are almost always insoluble. That's true, but sodium's 1A. That beats that out. That beats that other rule all the heck. All right. So this is soluble. Manganese 2 carbonate. So most carbonates are insoluble. Is manganese one of the exceptions? No, it's not. Only 1A in ammonium, remember? So this is insoluble. Potassium acetate. Soluble or not? Oh, it's soluble, all right. In fact, it's really soluble because K is a 1A and acetate is also always soluble. So it's super soluble, all right? And then number 8, magnesium hydroxide. Okay, so most hydroxides are insoluble. Exceptions? 1A, ammonium, calcium, strontium, barium. Magnesium is not one of the exceptions. This one is insoluble. Okay? Solubility rules. Make sure you learn them. Make sure you remember them. Okay, so I think we have gone as far as we need to go today so that you can complete your assignment for tomorrow. Again, so that is due tomorrow. So I think that's it. So until next time, this is Mr. Keister signing off. Take care, everyone. Stay safe. Keep working hard and stay focused. We are almost done, folks, for semester 1. We actually have one more lesson to go. All right. And so stick with it, folks. We're almost there. Take care and see you next time. So long.